Sort of in the middle of page 1 of our notes packet, we are going to describe some of the rules that dictate how we write electron configurations. So your electron configurations, when I say electron configuration, this is the kind of thing that I'm talking about. I do think we already went through all of this, didn't we? Yes? No? If we didn't, tell me and we can go over it. We did?
Yeah.
Okay. So on this page, this is basically just putting into words all of the rules that dictate how that goes. So an electron configuration is a shorthand method of writing quantum numbers to represent the location of all electrons in an atom. We do know that it's really, really hard to predict the actual location of electrons in an atom. So this is really only the case 90% of the time. And then A, B, and C are the Aufbau principle, the Pauli exclusion principle, and Hund's rule. I'm not going to test you specifically on the names of them. However, you are expected to know how to actually use them. So the Aufbau principle says that electrons enter orbitals of lower energy first. And then it just goes on to list all of the orbitals in order of lowest to highest energy. So your 1s energy level sublevel is going to be the lowest energy, which is why every single electron configuration will start with 1s. And then after 1s, you go to 2s, and then 2p, 3s, 3p, 4s. When we talk about something being higher in energy, that means that it's later on in the electron configuration, so this is all of them. Sometimes it doesn't necessarily make sense. So for example, if I'm looking at this one where I have 4f coming after 6s, normally we would think that 6 has higher energy than 4, but because 4f comes later in the electron configuration, that's what tells us that it has higher energy. That is consistent with what's on our periodic table that we drew. So remember when we went through, and yours should actually have all of them written, I remember giving time for that. As we go through and you read straight across from left to right, if you are following it in the correct order, then you'll get those energy levels correct. So this is the same thing as talking about 4s, then 3d comes after 4s. That means that 3d has higher energy than 4s. And then it goes back up to 4p. So later in the electron configuration, or later as you're reading your periodic table, means that it has higher energy. The Pauli exclusion principle says that no more than 2 electrons can occupy the same orbital, and they must spin in opposite directions. Again, we have already practiced all of these rules. We're just kind of tying words to it now. So we represent this in our orbital diagrams with the arrows. Did we draw orbital diagrams with arrows already? Yeah. Yes. It should be on this page, where each S sublevel has 1 orbital, each P has 3, F or D has 5, and then F has 7. Remember that? So that's our orbital diagrams. So Pauli exclusion principle is what tells us that we can only have up to 2 electrons, and they have to have opposite spins, which we represent as an up arrow and a down arrow. And then Hund's rule says that orbitals of equal energy must each have 1 electron with the same spin before any orbital is occupied by a second electron. So what this actually looks like is that if I'm doing, let's say, the 3p sublevel, this is just an example, and I have 3 orbitals, Hund's rule is what tells us that if this is going to be full, each one would have 1 electron with the same spin before anyone got a second electron with the opposite spin. Question?
I had a question about the orbital diagram. What happens if there's less electrons than there are orbitals?
Good question. So if I did that same 3p orbital, and let's say I only need to have 1 electron, then I would just draw the 1 electron, but you would still draw those 2 empty lines to represent your 2 empty orbitals. That is a really good question. So on your review, when you're answering questions, it will say something like how many orbitals are full, how many orbitals are half full, and how many orbitals are there. These would still count as orbitals that exist. They just don't have any electrons in them.
Okay.
Great question.
And it's like something like, I was just really confused.
Yes. Yeah, thank you for asking that. The other piece is that when I'm asking the questions about like what I just listed, how many orbitals are there, or how many orbitals are full, or how many are half full, take it very literally. I'm trying to be extremely clear about what it is that I'm asking for. It's not meant to be a trick question. Sometimes I'm asking how many sublevels are in a specific element, and sometimes I'm asking just how many sublevels exist. So just make sure that you're paying attention to how the question's worded. Do you have another? Yes, let me pause this real quick and I'll look for one for you. All right, and then the last part on this page is letter D, saying how is it written. So this is how we write our electron configuration. Like I said, we've already done these. It's no different. We're just tying words to it. So the large number represents the energy level, or that's sometimes called the principal energy level. And then the other thing that really confused people, maybe because it got cut off, is that is also sometimes written as the N equals something energy level. So on your review, I think there is a question that asks about that. If you see it, point it out. So when you see the large number, meaning like the 1 or the 2 here or the 2 here, that represents the energy level. Also known as the principal energy level, or the N equals whatever it is. So if I asked, I'm going to flip this over, but I'll come back. If I asked in this question, the way that it might be worded is I might say something like, how many electrons are in sulfur's N equals 2 energy level? And then you would just look at all of the things that have a big 2 in front of it, and you would add those up. So the answer would be 8 for that question. The small letter on this page, small letter represents the what? Do you remember what we called that? The S or the P, or sometimes D or F. Sublevel, thank you. And then the superscript, that means the same thing as the exponent. So if you don't know that word superscript, it's like the opposite of a subscript. That is exponent. It's not actually an exponent, it's called a superscript. That is the little number up here, so the 2 and the 2 and the 6. That represents the actual electrons. This is super helpful, and the number one surefire way to make sure that you know which element you're talking about is by adding up all of the superscripts, which tells you the number of electrons, and that will always, in this unit at least, it will always match the atomic number for that element. So for example, if I have 2 plus 2 plus 6, by adding up those superscripts, what's 2 plus 2 plus 6? That equals 10. So that's 10 electrons. That tells me that I'm going to be element number 10, which is neon. So it's going to match your atomic number every single time. There are no exceptions to that for this entire unit. There are cases where you could have an electron configuration for an ion, but that's not something that we're covering at all this entire lesson, so don't worry about that. And then how do you check? So the total superscripts equals the number of electrons, which is what I just said, which equals the atomic number. And then the last part of electron configuration identifies the location of the element on the table. So this is sometimes called the identifying square. I'm just trying to get you familiar with the terminology. So if I say identifying square, we're talking about what box does that element actually sit in. So for this one, if I'm looking at this and it's 3s1, this tells me I'm in the 3rd energy level. I am in what sublevel? S. And I am in what box? The first box. Perfect. So that is the identifying square for that element. if this is the element, if you have 2 plus 2 plus 6 plus 1 electrons, that would be 11 electrons, and that is sodium, Na. Which makes sense because I'm in the third energy level, I'm in the S sublevel, and I'm in the first box.